prosthetic, that is a device fitted to basically substitute for a lost limb. So they're, due to the high focus of lower limb prosthesis, especially in the medical sciences, has led to the various types of lower limb prostheses, which are fitted in accordance to a person's height, age, level of activity, but most importantly, they're divided or categorized according to the level of amputation. So it only makes sense that the higher the level of amputation, the more components are required. So if we were to divide them in accordance to those categories, we have the foot or partial foot prosthesis, which is basically only a foot and an ankle. And then we have below the knee, which is a prosthetic that is below the knee component. It does not involve a knee component, as opposed to the through the knee prosthetic, which involves a knee component that can bend and extend and can generate movement required for walking and sitting and running. And then we have the above the knee transfemoral prosthetic, which is basically a prosthetic, as its name suggests, that's above the knee. So, and along with the knee component, it also has a pylon or a shank, which you can see here between the knee component and between what is considered the hip socket. And then the most severe or the most extent type of lower limb prosthetic is the hip disc articulation, which basically involves all the components we can see in this figure. So we can see, like I said, the foot, so the pylon, which attaches the foot to the knee joint. We have another pylon between the knee joint and the hip joint, and we have the socket of the hip. So in addition to the different types of lower limb prostheses, we also have different types of feet. So we can see the first type here in the figure is a single axis foot. And as its name suggests, it only moves in one axis. So it only performs or generates up and down movement. So it only goes about the y-axis. In contrast to the multi-axis foot, which moves in three different axes. So it not only moves up and down, but it also moves left and right. And we have the third foot, which is a dynamic feet. And this type of foot is basically considered the most responsive kind of foot. So it's intended for users that require a very active foot that not only works efficiently in the means by which it moves, but it has a good energy return. So as you're walking using the dynamic foot, it absorbs energy that is generated through the gait cycle, as a human leg does, as a human foot does, and it returns some of that energy, so it's energy efficient. And the last foot here we have is a sack foot, and the sack is a well-known commercial foot, and it's known for its good price. It's very economical, and it has a heel cushion, which basically allows for a comfortable heel strike. In addition to the heel, which provides a stable mid stance. And now we're going to talk about the design of the setup and the different sectors that we actually executed in a thorough manner. We have first the structural design, and we're going to discuss what went into the decision of the dimensions that we used for the structure. And then the mechanical system design and the early models that we implemented, the decisions that we had to take to choose the mechanism that's well suited for our project. And then we're going to explain the data acquisition system, which as any acquisition system involves a sensing unit to acquire the physical environment, and an actual selection which receives the command from the data acquisition or the microcontroller itself, and generates a sort of function. And then so here we have the two main concept designs that we came up with for the structure. We have the first one is a movable ground design, and in this design we have, as you can see, there's less components than the design shown in figure 8. And in this design we have the knee component. We have the distinctive feature here is a movable platform. So this is considered the platform or the ground, and it's driven by and it has pistons that are driven by a motor and a gearbox. So what that does, it allows a vertical movement up and down, and that basically mimics the gait. So as the foot moves, the foot doesn't need to be movable because the ground is basically subjecting the movement on the foot itself. In contrast to here, where we can see we have a lot more components, we have a 4-bar mechanism. I'll explain what a 4-bar mechanism is in the next slide, but for now the 4-bar mechanism represents the hip. So we have an additional hip. We have the knee, which is driven by another motor. So we have two motors, which costs energy, but in return, this system is more flexible, and we're able to study more kinetic and kinematic aspects of the prosthesis itself. Also, we have a spring on the bottom of the platform, and what the spring does is it basically performs like a loading and a release on the foot. In addition to the structural designs itself, we came up with a ground that is movable, but in a means where it will save energy. And it has two distinctive features, and by that I mean, number one is the platform itself is driven solely by the impact of the foot, meaning it will slide backwards when the foot subjects onto the platform. So no motor is required for its movement. In addition, it also has inclination varying feature, where we can simply just shorten the industrial chain on one side, which causes some form of inclination, and that's really good when we want to correlate to the testing of prosthesis in grounds that are considered uneven and grounds that have some form of inclination, especially in Jordan. We know that Jordan's grounds are not very smooth, and the terrain is pretty hilly, as Mira mentioned earlier. Before we get into the mechanics of the system, we needed a reference, and by reference I mean we needed the movement or the projectile of a normal human foot. And to do that, what we did is we obtained the data sheet of a meat trial that our professor provided us with, and we basically plotted a graph of the cycle phase against the knee position. And the blue, as you can see, is the movement of the left foot, and the orange is the movement of the right foot. So the movement of the right foot in orange is what we use for the projectile or our reference, so that when we tried to obtain the mechanism we wanted, we looked at this trajectory and we tried to obtain a very similar one. So before we did that, so a four-part mechanism in general is a mechanism that consists of